Madam, please begin.
Yes, sir. Hello, welcome everyone. Thank you for joining us in today's webinar. I am Professor Vishaka Khambati, Faculty of Biomedical Engineering Department of PIT Parul University. Today we are presenting a webinar on applications of machine learning in medical imaging, which is presented by Mr. Bhaskar Pandey, sir. Currently, he is working as a senior researcher at Department of Electrical and Instrumentation Engineering, SLIET, Longwal, Punjab. Sir has completed his BTech and MTech in Electronics and Instrumentation Engineering from the SLIET College, and right now he is working as a senior researcher with the same college. He has a very good command on MATLAB, then Arduino, LabVIEW, SCADA, and PLC. So without taking too much time, I will hand over today's session to Sir. Sir, please start.
Thank you very much, ma'am, for that kind introduction. So let's begin without wasting any time. The topic of today's presentation, as ma'am said, is applications of machine learning in medical imaging. So let me just share my screen. So is my screen visible to everybody?
Yes, sir.
Okay. So the structure of today's webinar would be as follows. First, we would discuss about medical imaging, the basics, and machine learning, what it is, and deep learning. And without going into too much theory, because all the other webinars also go too deep into the theory, we don't have much time. So instead of going deep into the theory, we would look at some practical examples. If the time permits, we would look at one major application too. So the first thing is medical imaging. That is also called diagnostic imaging. So the question arises, what is diagnosis? So the diagnosis is identification of the nature of an illness or any other problem. This can be done by examining the symptoms, but not always. Sometimes symptoms don't always convey the truth. So doctors have to rely on some tests. These tests can be either performed by pathology like blood tests, urine tests, or some other things. But sometimes these tests can be performed using medical testing like MRI, CT. That way, a physician or doctor can get a look inside and what's really happening. So this is the steps. These are the steps that a new patient is treated, how he is treated. So the first step is consultation, and after consultation, diagnostic testing, treatment, and then follow-up. So if we look at the treatment steps, diagnosing is the second, and arguably it is the most important, or as important as treatment itself, because if diagnosis is wrong, the treatment would be wrong. So earlier what happened was diagnosis was entirely based on doctor skills and competency, because doctors used to complete entire treatments just based on Nadi Vidya or just according to their experiences. But sometimes these things failed, and this was not properly, there was no check back for this. There was no fallback the doctors could rely on. There was nothing that doctors could use as the secondary for their inputs. So proper diagnosis requires labs and imaging, but doctors had nothing. So these things made their way into the medical field gradually. And today we can see that there are a lot of testing and there are a lot of equipments and there are a lot of procedures for these things, for diagnostics. So what benefit this has caused? This has caused a great deal of benefit. As we can see in the graph, this graph represents average life expectancy. That is how long an average person of a country lives. So here we can see three countries. We have the red one, that is Canada. We have the green one, that is the US, and in blue we have India. We can see India lags behind Canada and US by almost 10 years. But still, we can see that India has made a rather impressive recovery. Like in before 1960, India's average life expectancy in 1960 was 41 years. That is, an average person in India in 1960 would just live up to 41 years old. And before independence, it was around 35. So we can imagine what the medical condition in the country would have been. But today, it's quite better. But for the lowest of the low, for the poor, and for the marginally separated sections, healthcare isn't as good as as we are having for ourselves, because there are a lot of problems. One major problem is accessibility. There is a lack of accessibility, there is lack of education, and there are many such reasons. And medical imaging, as we have already seen, that is very important. And many cities, many towns don't have proper imaging centers, don't have proper imaging technologies, proper imaging modalities, and patients have to travel a lot of distances. Patients have to endure a lot of pain and everything just to get the imaging done. So we can see imaging, how important imaging is. But with the advent of AI and machine learning, and with the improvement in technology, these things can be made easy, and these things can be brought to towns and villages too. So as we can see, the medical imaging refers to several different technologies that that are used to view the human body in order to diagnose, monitor, or treat medical conditions. Each type of technology gives different information about the area of the body being studied or treated, related to possible disease, injury, or the effectiveness of medical treatment. So the first imaging technique that was introduced to the world was X-ray. It was introduced in 1985 by a German professor of physics. His name was Wilhelm Röntgen, and there is a unit named after him too. X radiation or gamma radiation unit, Röntgen, is named after him, and he invented X-ray in 1895. And there are many such common modalities that we still use, like X-ray and CT and MRI, ultrasound. These are the basic imaging modalities that we use in hospitals around the world, and they are so common that they have become a part of our everyday lives. But what happens is, not everybody can read an X-ray, and doctors are overloaded in this country. India has one of the lowest doctor to patient ratio. Why is that? Because India has such a huge population and less number of doctors. So doctors are overloaded, and diagnosing from a report is also a doctor's job. But sometimes doctors also commit mistakes, but that is not the point right now. The point is doctors are overloaded, and this load can be reduced by automatic diagnostics of these modalities using MI or ML or AI. So what is diagnostic imaging? Medical imaging literally aids the physician to understand the complication in human body and enable them to take better decisions. So medical imaging generally produces completely painless, non-invasive. Most of them don't require any special preparation. So what are the use cases? The first is better patient care. The first is better patient care. Because of medical imaging, patient care has improved a lot. And the second is complicated surgeries. If a doctor or a surgeon is going to get inside our body, is going to make an incision, the first thing he would prefer is to make as minimal invasion as possible, because in today's medical world, minimal invasion surgery is being preferred. So small incision, as small as possible, is preferred. So to make that feasible, doctors have already an idea that what they have to do and where is the problem and what are the complications around it. This has only become possible because of imaging modalities. Because due to imaging, doctors already get an idea. They already know what's inside and what they are going to operate on. As compared to earlier, when doctors only found out what the problem was after opening up the patient. So this has given a lot of confidence to doctors, and this has improved the quality of surgery and thus the quality of life for many people. So, and the next is affordable healthcare costs. Medical imaging is costly, but in the long run, healthcare costs are reduced due to this. How is that? Because if we just discard imaging and we go directly to treatment, this can be beneficial for some, but for most, that treatment would be wrong. And they will have to repeat the step again and again until the right treatment is done, or there is a major disaster and something bad happens. So in the long run, for proper treatment, affordable healthcare costs are uh, are there with the use of imaging, and this it is safe and effective. Medical imaging, there is a radiation factor. Radiation is there, but that radiation is being reduced and it has reached a safe level. And researchers claim that these radiations do not harm much. And the next is file sharing ecosystem and data privacy. So with the help of imaging, there is a file sharing ecosystem, and patient records are now kept online, or they can be forwarded to another doctor when the need arises, and everything like that. So what is the direct need of AI in medicine? AI is, no matter the industry, AI has become commonplace. When it comes to medicine, AI helps practitioners a lot. Like large tech companies are investing more funding into AI healthcare innovations. For example, Microsoft announced a 5-year, $40 million program in 2020 to address healthcare challenges. So, although AI is doubtlessly changing the healthcare industry, this technology is still relatively new. As AI adoption expands throughout the healthcare sector, questions about the advantages and limitations of this technology become ever more pertinent. So, let's look at a few of the benefits of AI in medicine. The first is it provides real-time data. Like when the imaging is done with the help of AI, instantly we can get the results. Now what happens? We get the imaging done. Then that image goes to the radiologist studies and then diagnoses. And that diagnosis could also be wrong because humans make error. So AI also makes error. That I'm not saying that AI is 100% accurate, but it won't make any non-linear error. Everything would be same according to it. It won't tire out. It would perform the same every time, right? And second most beneficial thing is streamlining tasks. With the use of AI, we can make everything automatic, like appointment booking, patient status inquiry, and everything. So AI saves time and resources, and it may reduce physicians' stress too. So let's come to the second section of the webinar, that is machine learning. So machine learning is a branch of AI and computer science which focuses on the use of data and algorithms to imitate the way that humans learn, gradually improving its accuracy. So basically, machine learning is nothing but statistics. Uh, statisticians have been working on these problems for a long time. When we look into this, some of the classifiers, some of the algorithms that we are studying today, they were developed in 1930s, 1940s. So it's the culmination of all those hard works into that we are using today. So machine learning is of great use today, and it is being implemented in very intimate parts of our lives too. They are being included in almost day-to-day activities. For example, like separating spam from actual emails. So this is also being done with the use of machine learning, as we can see in Gmail, and correcting grammar and spelling mistakes as seen is autocorrect, and also word suggestions. If we are typing in our phone suggests what we are going to type next. This is also a NLP problem. So that is also a machine learning problem. So machine learning is good for object and image recognition, detecting fake news, understanding written or spoken words, and like bots on websites that interact with humans, like Alexa, and many more. And there are many more bots that were launched. For giving an example, a bot was launched by Microsoft, and that bot had to be closed after 2 days because in 2 days it was acting like an average Twitter user. It was making everybody uncomfortable by spitting out uncomfortable comments. So in 2 days, it learned to act like an average Twitter user, just like that. And there are self-driven cars too. So what are the basic steps of machine learning? The first is data collection. So the data is important to train the machine, and then preparation of the data. We have to select the features. We have to scale the data, and there are many such steps. Then we have to choose a model, what we are using, and then training the model, evaluation of the model, and parameter tuning, and lastly, making predictions. So let's get to our first example of hands-on machine learning. So there is this dataset called IRIS dataset. This dataset is termed as the hello world of machine learning. Like in any programming language, C, C++, Java, Python, when we start to learn that language, the first thing that we do is print hello world. So similarly, IRIS dataset is termed as the hello world of machine learning. What happens in this dataset is there are 4 features. There is a flower called iris, and there are 3 types of iris: Iris setosa, Iris versicolor, and Iris virginica. So we are taking 4 attributes or 4 features, and those are sepal length and sepal width, petal length and petal width. So we are taking these 4 features from the flower, and then we are going to classify according to these 4 parameters into these 3 flowers, whether it is Iris setosa, whether it is Iris versicolor, or whether it is Iris virginica. So for this, let's move to MATLAB. So is MATLAB visible to all?
Yes, sir.
Okay. So this is the IRIS data set here. As we can see, we have 4 attributes, and these attributes are sepal length, sepal width, petal length, and petal width. And this here is the target. So target is the output. So this is the first 50 is Iris setosa. The next 50 is Iris versicolor, and the next is Iris virginica. So we have 150 data here, and we can train this. For this, we can just write a bunch of codes, or as simple as we can open classification learner in MATLAB. This is the pre-built application used in MATLAB, and this classification learner application can be used to train many models simultaneously. As we are going to see, we are going to import the IRIS dataset from our workspace, and we are using columns as variables. That we have 5 columns, 4 columns are variables, 1 column, that is column 5, is our target. And we are going to use hold out validation 20%. And once we click on start session, the data is loaded. The data is being loaded, and once the data is loaded, we would see a scatter plot. Like this is the scatter plot here, and we can see this is the scattering of data. So here we can see 1. 1 is Iris setosa, 2 is Iris versicolor, and 3 is Iris virginica. This is the plot between column 2 and column 3. That means column 2 is sepal width, and this is petal length. If we discriminate against these 2, we can clearly make a distinction. We can clearly see that one is different than the others. So this is a very basic problem. And in MATLAB, we can do it as following. We can just go here. We can choose all networks. If there is a fast processor, you have got a fast processor, you can choose all. You can you should select parallel processing if you have got a GPU. And once connected, clicking on train, parallel pool is starting. That is, GPU is also starting. And once it is set, all our models would be trained simultaneously, and we can see the results. We can see the confusion matrix. We can see the ROC curves. Okay, so parallel pool has started and the training has started. And the models are being trained here. Every model that is available in MATLAB here has been trained. And we can see the results. Like Pine Tree, there is accuracy of 86%, 86, and linear discriminant model has an accuracy of 100%. This sometimes happens, but this is an easy data set. And quadratic discriminant also has an accuracy of 100%. SVM, normal linear SVM, has an accuracy of 96%. And if we want, we can also look at the confusion matrix, or we can look at the ROC curve and everything. So this was the basic use of machine learning in MATLAB. And this was a very basic data set, iris data set. So we can have any data set that we want. And the data set should have some features. The first thing that the data set should have features. And selecting features is very important. Selecting features is called feature engineering. So, for example, what we are going to discuss is brain tumor detection. Like there is a brain MRI image and there is a tumor on it. And that tumor is clearly visible. It's white in color and the brain matter, rest of the brain matter is dark in color. So that tumor is clearly visible. But how can we discriminate on that? Using machine learning. So what we do is we take out features from that image. We take out features of that particular tumor part. And those features are like contrast. Those features are like mean, median, mode, and 7 such GLCM features. So these features we take out and then we train the model on those features and we give a target as to if the image is cancerous, if the image is malignant or benign, then the answer is this. If the image is that, then the answer is that. So we train the model like that and we make predictions on that. Okay. So this was a basic example of iris dataset in machine learning. And then moving on to deep learning. So what is deep learning? It is a type of machine learning based on artificial neural networks in which multiple layers of processing are used to extract progressively higher level features from data. And as we can see, deep learning is a subset of machine learning, right? And machine learning is a subset of AI. So here we can see in the image that feature selection is not present in feature extraction, is not present in deep learning. It is present, but it is inside the layers. So this signifies that in deep learning, feature extraction or feature selection is automatic, but in machine learning, feature extraction is manual. So this here is an advantage if we are using a large data set or we are not sure about the features. For example, if we are trying to detect cats and dogs, so how can we describe the features of cats? You can say big ears, or they are cute and the dogs are not, and then some would say that dogs are cute, cats are not. So the feature defining process is not too easy for this. So what we do in deep learning, we just give this task to the model itself. Model itself recognizes features according to the images. It takes the features into account, it takes the background into account, it takes the brightness or contrast of the images into account and everything. And once after we have given a large enough data set, the model would get a complete picture and it would detect properly. But in machine learning, we would have to extract the features manually and give it to the classification algorithm. So this is the list of major differences between ML and deep learning. So the first is volume of data. Machine learning can easily work on thousands of data. But when it comes to millions or even billions of data, because now is the age of big data analysis, every industry or every company is working on data. Our data, that we are just their products. Our data is their product. And everything is tracked. If we go into a shopping app and we get back from the cart or we don't get back from the cart, every step, our every click is recorded and saved. From which page we got back, from which page we went where, from where we searched what. So everything is recorded, and these data, billions of rows are being generated every day, and these have to be treated by somebody. So that is big data analysis, and that is the peak of machine learning and deep learning right now. But machine learning fails in that, in big data, because why is that? Machine learning models they need enormous computing power to handle such levels of data. And deep learning can handle those levels of data easily. They also require a large amount of computing power, but they can handle those. And the next is training time. Machine learning models take less time because the data size is small, and deep learning takes a huge amount of time. The next is feature engineering. The major thing here is that we have already discussed that humans have to do feature engineering in machine learning, and in deep learning, there is no need for feature engineering. Neural networks automatically detect important features. Then human involvement, machine learning models are easy to build, but require more human interaction to make better predictions. And deep learning models, they use complex multi-layered neural networks, but they have the capability to learn by themselves. And performance, machine learning models perform on small and medium-sized data set, they perform good. But deep learning models perform on huge data sets. If we train a deep learning model on a small data set, it won't perform as good as machine learning. So for this example, we are going to use cancer dataset. This is also incorporated into MATLAB. This dataset can be used to design a neural network that classifies cancer as either benign or malignant, depending on the characteristic of the sample biopsies. So this dataset has nine features and one target. So those 9 features are clump thickness, uniformity of cell size, uniformity of cell shape, etc. And the targets are either benign or malignant. So what here is after biopsies of cancerous or some excessive growth, the properties of the biopsy tissues were recorded, like the clump thickness, uniformity of cell size, and 9 such characteristics were recorded. And once the biopsy confirmed that the tissues are either malignant or benign, so those targets, those outputs were recorded. And with this information, we have to train an artificial neural network. So in MATLAB, we are going to train an artificial neural network. But this here is what we are going to do in this example. We are going to train a shallow neural network. And what is the difference between a shallow neural network and a deep neural network is shallow neural network has only one hidden layer, while deep neural network has more than one hidden layer. So this is the cancer data set, breast cancer data set, and here are the 9 features. This is the method that we can do, import the data sets. This is the input, cancer inputs file. You can see it here. These are the these 1, 2 rows are features here, and these are the samples. So we have got 699 samples per class, and we have 2 classes. One is malignant or benign. Either the cancer is malignant or benign. So this here gives us the option to set the training size, validation, and testing size. We are going to set 70, 15, 15. 70% data is going to be used for training, 15% for validation, and 15% for testing. And this option lets us set the size of hidden neurons in the hidden layer. How many neurons are going to be there in the hidden layer? We can set it from here. So let's keep it at 10 for now, and let's see what our results are going to be. This is as simple as that. We just train a artificial neural network model in MATLAB. You just have to click train, right? And the model is trained. The model is trained. It took 16 iterations, 16 epochs, and the performance is listed here. This is the cross entropy. This is the error percentage. So we can see this error, and what you can also see is error histogram. The performance like this shows the training and testing performance. So the blue line is the training loss, and the training cross entropy during training. The less the better. The less the value, the less the better. So what here we can see is during the first epoch, during the first iteration, it was high, but as the epochs increased, it reduced, but it is still too high. And then after training the model, we can see the model is not too good. So we can tune the parameters of the model. This is called hyperparameter tuning. And what we are going to do is one such thing, we can increase the number of hidden neurons. We can just make it 100 instead of 10. And where this was in the order of 8, now let's see what's the order of this. This time we can see it is less than 40% of what it was before. So it performed better, much better than before. We can make it even better, I think. Do you think we can make it even? Let's increase it to 500 and let's see what happens. No, it became worse than before. So what happened here? This thing is called overfitting, right? So there is some problem with using too much of data and too little of data, underfitting and overfitting, and best fit. These things happen. So here overfitting happened, right? And this made our results worse. So the best result we got was at 100. So increasing the hidden neurons is not always good. We have to, and there is no set number that for what application, what would be a good number. This is just hit and trial. We just have to check it by just performing our tests. So this was the data set, and this was how we train a shallow neural network. This neural network was shallow. This was not deep. This was shallow because only one hidden layer was there. So moving on, we just did the example of cancer dataset, and this was MATLAB and its basics. Now, these things can also be performed on Python, and Python is versatile. It is very versatile, and it is the go-to language for this. So MATLAB has its own uses and own advantages, and Python has its own. Both are very good in their own. So let's take a look at Iris dataset and basic code in Python. So this here is Google Colab. Google Colab is a free environment developed by Google, and it runs Python Notebook. Python Notebook is a kind of program where we can write text, where we can write equations, where we can write everything along with codes, and these codes can also run. So as we can see, what here happening is the first step is to import libraries in Python. That is very easy. Python is very easy language because it is very close to what we speak. Like we are importing NumPy. NumPy is a library for MATLAB like matrix multiplications in Python. So we are importing NumPy as NP, and Pandas is a library for data frames or handling data sets, making tables out of data sets, and Plot9. This is a library for plotting graphs, and sklearn, scikit-learn. This is for machine learning models. So the Iris dataset is hosted at this URL, and we just give this URL to data URL, and we define the columns, feature columns, sepal length, sepal width, petal length, petal width, and the target columns. So we just download this. We download this data set, and what happens after? We get this in response. The rows are split into this, and the data is split by comma for rows, and we create a data frame using PD, that is Pandas library. And after the data frame is created, features are set as float category, and the target column is set as category, that it is the class or it is a category of output. So df.head gets us the output or the top 5 values of the data frame. So we can see this is the serial number. This is not counted. This is the heading. This is also not counted. What is counted is this. This is called dataset.values. We have 1, 2, 3, and 4 features and 5 samples because we use data set head. If we use df.tail, we would get the last 5 data. And describe, df.describe, data frame.describe gives us the count, mean, standard deviation, and basic statistical values of the data frame. So this is called data visualization or data exploration, because we are first looking into the data of what the data is, what we are going to treat, what we are going to predict. So it is also important to look at the data. And there is the next thing called data pre-processing. And what pre-processing is? To make the data better. If there are outliers, if there are bad values in the data, we have to replace that. If there are any missing values in the data set, we have to handle that. So these things are called data set pre-processing. And here we have the scatter plot like it was in MATLAB. This is the same thing. We are doing this in sepal length versus petal length. And there also we have seen that iris setosa was very different than these two. So it is easier to classify iris setosa, but these are somewhat overlying, so it is a bit difficult. So we import a basic scikit linear model for logistic regression, and we just use the line model.fit to train the model. And what is x and y? X is the features and y is the target. And model.fit x comma y. This line alone trains the model. There is nothing too much to that. And after that, we calculate the accuracy. So for here, the logistic regression model, HLR model's accuracy is coming as 97.3%. And this was the prediction. This red was falsely predicted. It falsely predicted, and all the blue was correctly predicted. The circle is iris setosa, triangle is iris versicolor, and the square is iris virginica. So this was iris data set in Python. And the last thing that we are going to discuss is a complete example of deep learning model. Classification of X-ray as COVID or normal X-ray. So this follows the exactly same steps. First, we import the libraries, but what here we are doing is we are importing Keras. Keras is a TensorFlow library developed by Google for deep learning purposes. So it makes making deep learning models very easy. It makes making deep learning models very easy, and we can add or drop layers with just a line of code. So we are copying a data set from GitHub, and we are doing all the requisites, and let's go through the code line by line. First step is importing libraries, and as the need arises, we just type this from the library, the module and the name of the library. And we are also importing CV2. CV2 is OpenCV. OpenCV is a open source software Python to read and display and train images. So this is a very useful library if you are going to use image processing. And NumPy, as always, is for MATLAB-like matrix manipulations in Python. And ls. So we can see here, if we run the code and if we delete this folder. Right. And this git clone command would copy this GitHub repository into our Colab environment. And this would take some time depending on the speed of your internet, but After that, what we can do is we can look inside in the folder and we can see we have data set. And inside the data set, we have 3 folders: evaluation, testing, and training. So evaluation has 1 image, one for infected and one for normal. Similarly, for testing, we have some images for infected as well as normal. And we have the most images for training, for infected as well as normal. So we will just go through the folders. LS is list what are the folders in this. It listed that in this directory that we are on presently, we have 2 folders. One is classification of COVID-19 chest X-ray images, this folder and this folder. Then we changed directories, CD change directory, we got into this folder. Once we got into this folder, we again did ls to list the contents of this folder, and we got this. Then we know the data set is in data set. We got into data set, this folder here. And once again, we listed this evaluation, testing, and training. And we got into training just to, these are the basic file operations that we can perform in Colab or in any Python language. So these are the image paths that we have given, like training, normal path. So this path would be inside training and normal, right? And infected, train infected, we would give infected within training, and then test normal, test infected, evaluation normal, evaluation infected. This is how we give the paths. And now we listed how many number of images are in each of the paths. So in the first path, train normal, we have 297 images. Train infected, we have 296. Test normal 69, test infected 25, and we have 1 image of normal evaluation and 1 image of infected evaluation. So we can see we have kept the training images approximately same. So this is a good practice to keep. If we have 2 classes or we have more than 2 classes, we should try to keep the number of images same for each class while training. So we resize the image into 224 cross 224 because the images can be in multiple size, and the model that we are going to make, the input layer of the model would take the image into a particular fixed size. So we beforehand crop the image into the fixed resolution. We crop it into 224 cross 224. And we display the images path. Every image is displayed here for training as well as testing. All the images listed here. And then we can see the data.shape, how many images that we have. We have resized images 224 cross 224 cross 3. This is the size of 1 image. This is length, and this is width, and this is number of page, RGB. 3 pages for RGB image, and this is the number of images. And these are labels. So with this code, we added labels to every image. Whatever folder it was in, that was its label, because we, while training the model, we have to give the model an input. Like if we are giving a normal X-ray image, we have to tell the model that it is normal. If we are giving the model infected image, we have to tell the model that this image is of an infected person, so that the model can accurately predict. So as we can see, the labels are in the same order as these images are. So that is how the model can connect. So this was the image, and this, it was infected. And if this was the image, it was normal. So after training on 266, 267 images for both the classes, the model would get to know everything. And we binarize the label. Label binarizer is a tool, a library that we use to binarize the label. Label binarizing means we would give a number to the label 0 and 1 instead of infected or normal. And after doing this, we can see the shape of, we have also split the data set into train and test. Because we combined all the images, we combined all their labels, and then we are randomly splitting. Every time we run the program, this part would be random. So randomly training data and testing data would be split using train test split command. And we can see we can set the number 20%. We are using 20% of the data for testing and 80% of the data for training. We can change it here. And so we can see the data, whatever it is. We can see 551 images are being used for training, while 138 are being used for testing. This here is the deep learning model. This is the pre-built model, VGG16. This is the pre-built model that we are using. We are doing nothing. We are just importing this model. This is the command VGG16, and this model is already there. And we have to do nothing. We have to just give the model, give the details of the layers, dense layer 64, dropout, and then output layer as dense again. This is the number of hidden neurons that were in this layer. And we define model checkpoint, like while training, the best recovered result, the best received results would be saved in checkpoints, and early stopping if the loss becomes too high or if the patience of the system is decreased. So then the training would stop. And this is during the training. Here we can see the line model.fit. As we had seen in machine learning application, the only thing that we use to train the model is model.fit. In here also, in MATLAB also. So we use model.fit, and we used input validation data, we use the training data, train X, train Y, we use the batch size and steps per epoch. We have used, give everything to this. We use 25 epochs, and this here was the result after training. What was the result? We can see during the first epoch, that is during the first iteration, the accuracy was around 97, and then the accuracy stayed in this range only. But after the final training, we got the accuracy of 97.61. This was rounded off and written as 0.98. So this was the accuracy of our model. And this here is the confusion matrix. This was on the validation data set, that 62 images of class 1 were classified as class 1, but 1 images of class 1 was classified as class 2, and 73 of class 2 was classified as class 2, but 2 were classified as class 1. These are the errors, 1 and 2, and 62 and 73 are the correct predictions. So this was a method to use pre-built model. We can just import the model and use it. What if we are trying to build our own model? So there is, it is not a problem. Every step would remain the same. Every step would remain the same. What would change is just this. We would create a new model. So we are not importing a model. We are not using a pre-trained model. We are just going to build a new model. And first we define the type of the model, that is sequential. A sequential model is where the input of a layer is the output of the previous layer. So just one after the other, that is sequential model. So using model.add, we add a convolutional layer, and then max pooling layer, dropout layer. We again add a convolutional layer, max pooling, dropout, convolutional. This is up to us how many layers we want to add. And all these things, a lot of research is being done, but till now, what works practically is using hit and try. There is no correct way to get the prediction at how many layers we should keep. There are some formulas, there are some tricks that work, but not always. So after adding all these layers, this here is exactly the same. Checkpoint and early stopping parameter and model.fit is also the same. So everything is exactly the same, but instead of using a pre-trained model, we created our own, and using just these few lines. So creating a model in Python is very easy, extremely easy, as we can see here. So after training the model for the same number of times, we saw that our accuracy was 60%. So what was the problem here? Nothing. We have to just do hyperparameter tuning. We have to improve our model. We have to try and try again until we get the best results out of the model. and we can look at the confusion matrix of the model. We can look at the training plots of the model and everything. There is also a plethora of models. There are many models for image classification, like that too made by very big companies. If we search on Google, TF2 Zoo, this is TensorFlow 2 and detection models. These are pre-built models developed by Google and other huge companies, and we can see their characteristics. So we can use these, we can use any of these models for our project, for our research work. These are all open source, these are all free to use. So we can use any of them for our projects. Every model has its own benefit. Some are fast and some are very accurate. Like this here is POCO MAP. What is POCO? POCO is a Microsoft evaluation matrix developed by Microsoft, and MAP is mean average precision. So the higher the better, and this is the speed, right? So in milliseconds, the lower the better. So the model would perform best if it is very slow speed, or the model would perform best according to our needs. If we want speed, we would choose a model that is greater at speed, or if we want accuracy or precision, we would get a model that is more precise. And these are the outputs of the models. What the model outputs: boxes or key points. Boxes or key points. What is the difference between boxes or key points? Boxes are just bounding boxes outside the detected objects, while masks or key points are exact locations of each pixel. So this here is any model. We can just click on it, it will be downloaded, we can use it. So let's get back to the PPT. Right. And we have also looked at the classification of X-ray as COVID or normal. And this was all in the webinar. Any questions?
Hello.
Yes.
Thank you, sir. You have covered almost all the things, like you have covered theory part with real-time practical performances. So this all things are very useful for our students. Thank you so much, sir, for giving your valuable time and sharing fruitful information with us. So, sir, is there anything else you wanted to cover before a wrap up?
No, thank you for inviting me. It's been a wonderful experience. And thank you all.
Thank you so much. Thanks to Parul University for giving me an opportunity to hosting this type of webinar. Thanks to PU Webinar Cell for technical support throughout the session. Thank you, everyone. Once again, thank you, sir. We'll see you next time.